Hello everyone. I am going to narrate this video which shows one way to run a TLC experiment. TLC, thin layer chromatography. Now it says here that the surface of the TLC plate has a lot of silicon hydroxyl groups, which makes the surface very polar. Therefore, the more polar molecules stick strongly to the plate, and they move less actually. We are going to put dots with a pencil about 1 centimeter from the bottom. That's where we're going to spot the samples. We want concentrated tight spots. Boy, this guy's going fast. And we're going to check the spots by UV before we develop the plate. So those are the 3 spots because we have 3 samples to run. Sample A, the mixture, and sample B. And we're going to label it. It looks like from B to A plus B to A. Now we're ready to spot the plate. Oh, we do have an acetone wash. We're using only 1 spotter, so we have to wash in between each sample. It looks like you dip and blot 3 times. We're going to start with sample B. And you're going to dab once, quickly, and then air dry. And I suggest dab a second time. Okay? So 2 dabs, but make sure you air dry in between the 2 dabs or else you're going to get a gigantic spot. We want tight, concentrated spots, not large, dilute spots. Let's try this again with the mixture of A plus B. Ultimately, this TLC is going to maybe confirm purity and or confirm which sample is more polar, which sample is less polar. Okay, wash 1 more time before we spot sample A. We want to check the spots before we develop the plate. If the spots are too dilute, we can spot more. If the spots are too large, well, we may have to respot the plate. But we want to check before we take the time to develop, to catch any mistakes before we spend a lot of time waiting for the development. So we are going to check by UV. This lamp has 2 settings, short wave and long wave. We're using the short. And the spots haven't moved. They're still at the bottom. We're just looking whether they're nice and uniform, round, tight, thumbs up, okay? If we didn't see any spots, it's too dilute, and we would respot on top of them again. We're going to develop the plate in a beaker that has a filter paper in it. That filter paper helps draw up the solvent so the surrounding air is moist. We don't want a dry environment or else the solvent will never travel up the plate. It will just evaporate off the plate. It looked like we're going to use a solvent that is 10% methanol dissolved in dichloromethane. Go ahead and eyeball this. You want to add enough solvent. Well, you don't add too much solvent so you submerge the spots. You do not want to submerge the spots. So it's going to be a little bit hard to tell, but look very carefully where the solvent touches the plate. It's still going to be below the 3 dots. If you could tell right now. See, the solvent is still below the 3 dots. Cover with a watch glass, and now that solvent is moving up through the dots. We're going to develop till the solvent front is about 2 centimeters from the top. Afterwards, we're going to calculate the retention factor, and the less polar molecules have larger RF, meaning the less polar molecules travel further, the more polar molecules travel less. Okay, so there was a time jump. Do you see where the solvent front is right now? It's closer to the top. That was probably 5-7 minutes. You're going to have to be patient. Now, immediately, once you take it out of the chamber, mark where the solvent front is before it evaporates. Okay? Oh, that's a pretty good guess. 2 centimeters, almost. Exactly. That top line that you just marked is called the solvent front. And you'll want to mark it immediately with pencil once you take it out of the chamber. I think that is one of the more common mistakes. The solvent front evaporates quickly, so you don't know where the solvent ended unless you mark it immediately. Those 3 dots, that's called the origin. We use 10% volume to volume, methanol and dichloromethane, and I like to write the TLC conditions at the top of the plate. What's next? Oh, we're going to check the spots. The more polar molecules stick stronger to the plate and travel less. The lower the spot, the more polar the molecule. The less polar molecules have larger RF, meaning that they travel further up the plate. Okay, so higher spots less polar, lower spots more polar. Cross your fingers. That's a good result. I like the fact that the middle lane, lane AB, looks like it has both spot A and spot B. You and your partner are going to circle the spots. Put a dot in the middle of each spot because that's where you're going to measure to. Right? We measure to the middle of the spot, not the top and not the bottom. Can you tell now which molecule is more polar, A or B? Let us calculate the RF value for at least one of these spots. There are 4 spots, so eventually you're going to need 4 RF values. And we're doing the first calculation for a spot in lane B. 1.4. Oh, and then we're looking at the solvent front, which is all the way up at 4.5. Did you notice that your RF value has to be less than 1? Unless the spot traveled with the solvent front, which is very rare. So it's going to be less than 1. It's going to be a decimal. And I'm probably looking for my calculator right now. Oh, what that means is that the spot moved about 1/3 of the way up from the origin to the solvent front. And I suppose this person's going to do the RF for the other spots, maybe? For A and B... yeah, I said that already. You're going to report 2 RF values. And then A will have the larger RF. It traveled about halfway. Maybe it's 0.5 something for lane A. And we are concluding B is blank. Alright, you all decide. Is B more polar or less polar than A?